Oh, sorry, Zoom. There's some questions on Zoom saying that they cannot hear us, so we just fixed that. If we categorize the physical world knowledge into 2 dimensions, then we could firstly figure out the knowledge that is only about the first single step perception, and this is the static knowledge. So we could focus on the object knowledge, for example, whether the object is existing or not, and we can also focus on some law of physics and also try to track the changes about the status. And on top of that, we want to figure out more details. So we think more about the objects. And then this is the object properties. And also we want to link it to the events so we can focus on the object affordance. And on top of that, we also want to figure out the connections between multiple objects. So that's the spatial relationship. And on top of spatial relationship, we also want to figure out how multiple objects are interacting with each other. So this is not only pair of objects, we also want to focus on the situation behind the scene. And this situation is related to the image information. If we extend it to the video side, then it's more about the temporal side, whether we could track the state changes, whether there's action related to that video. And on top of this single action, we also want to figure out the temporal relationships between multiple actions. And on top of these multiple actions, we can do long horizon planning. So if there's some new task, we can also figure out whether there's multiple actions involved and how is their temporal dependency can be. So this is how human can learn from the physical world. We basically focus on this different knowledge. For machine side, we also want to do the similar thing. So machine side, we want to learn the large language model and the vision language model. This model also needs to capture the physical world knowledge, as we mentioned earlier. And when we try to learn this kind of knowledge, we can mimic how humans interact with the physical world. So we could get signal of multisensory interaction. Unfortunately, recently, when we try to train these foundation models, we actually skip this multisensory interaction step, but try to use the static data to learn these foundation models. So we have large-scale images, videos, text, and other metadata data. And we mimic this kind of interaction by this static data. For example, if we have a video, then we could treat it as a visual recording of real world state changes. For example, if we know the book is falling down, then we could track the state changes. And then we use this data to learn the visual foundation models. So here we can see we got a lot of impressive results regarding different tasks like video understanding and image understanding, and also retrieval tasks and captioning tasks. But this kind of task, we got very high score, but whether that score really means that we have achieved very good abilities in understanding the real world can be a question. For example, there are a lot of probing tasks, or there are a lot of papers recently trying to show this kind of model cannot understand a lot of aspects related to the physical world knowledge, like in the verb understanding task. So if we just ask the model to retrieve the verb specific information, and we can see the performance is like not much higher than random performance. And another thing is that this kind of model really try to treat the sentence, the text side and the vision side as bag of words. So given this image, it didn't recognize whether it's the grass is eating the horse or its horse is eating the grass. So this is very terrible error. And another dimension we mentioned is about temporal dynamics. And we can see there are also recent publications related to whether single frame can already solve the benchmark. And we can see the single frame performance is quite close to the state-of-art performance, and it can also outperform the state-of-art performance if we make a lot of changes to leverage full information of the single frame. Basically, we have good model to capture the object-related information, but we didn't achieve good ability to understand the situation, to understand the action, and to understand the temporal dynamics. As a result, if we want to move forward, we want to move from surface to deep understanding. So by surface understanding, we focus on the object-centric understanding. And also this kind of information can be static. But if we want to move forward, we want to focus on the deep information that can capture event-centric information, and we can understand the situation, and this can be dynamic. As a result, if we want to achieve this goal, we want to add the knowledge understanding ability to these large models. So basically, we can focus on 3 types of knowledge. The first kind of knowledge is factual knowledge. So here we define factual knowledge as the facts we can extract it from the data. So these facts can relate to the entities, can relate to how these entities are connected through relationships, and also whether these entities can compose to some situation, whether we can recognize what event is happening in the image or video. And then we also want to recognize a lot of properties and the affordance related to information. So this is a map to the taxonomy that we mentioned earlier, that we will cover the object information and also how the interaction will go among objects. And in this entities, in this factual knowledge capturing, we can see that there are a lot of challenges in capturing the situation and action level information. So in this tutorial, we will also emphasize like whether we could leverage situation information or action information to capture multimodal knowledge through vision language pre-training. And this can help us to solve the challenge about capturing the complex situation in the real world. And another type of knowledge we want to focus on is not about instance, but it's about common patterns. So given a lot of historical instance, maybe we could try to summarize what is the recurring patterns among them. So this kind of pattern can be in different kinds of formats. One common knowledge that we leveraged a lot is common sense knowledge. So we have a lot of knowledge related to physical world or related to the like procedural planning. And another kind of format is the knowledge base format. So we also have external knowledge base that's summarized by human, and we can leverage that as some common knowledge to help with the learning. And this kind of common pattern knowledge will help us to do planning and to understand the temporal dynamics. So this will help us to understand the long horizon tasks, especially related to like robotics. And the last type of knowledge we want to focus on is the parametric knowledge. So nowadays we have large language models and also large vision language models. These models we have shown that there are a lot of knowledge has been stored in these large models. So this parametric knowledge is a new type of knowledge that we want to focus on in the next few years. And this kind of knowledge, in this tutorial, we will focus on whether we can distill it from language models. And then this kind of knowledge, whether they can be helpful for the vision language pre-training. Another direction is that we want to know whether we could distill this knowledge from vision language pre-training models. If we want to achieve this goal to learn this kind of 3 types of knowledge, then there's some interesting solutions that coming up recently, especially with the strong power of the large language models. For example, now we have very strong large language model that can help us to do the compositional semantic structure discovery. And another ability from large language model is to do long context reasoning. So this kind of 2 advantages maybe can help to solve the 2 challenges that we mentioned earlier for the vision language knowledge modeling. As a result, in this tutorial, we will structure it through these 3 types of knowledge. The first kind of knowledge is the factual knowledge, and we can see whether we can patch this kind of factual knowledge understanding into vision language pre-training models. And there also there are a lot of recent progress on this domain that we try to add the knowledge into pre-training models. So for the first session about whether we could add the factual knowledge into pre-training, we will focus on 3 types of knowledge. So we will focus on the entity level knowledge. So this is the most well-researched domain. And another type of knowledge is about the structures, like we try to figure out how objects are connected and whether they can reflect some event information. And another type of knowledge is the physical world knowledge. So we also want to focus on the affordance, and maybe we can use this multimodal prompt to help the embodied AI side. And for the second part of the knowledge, the common pattern knowledge, we will focus on the pattern that we can discover automatically from the historical data. For example, this is the pattern about making the cheesecake. So we will firstly try to make the crust, and then we will bake the filling, and then we will bake them together. So no matter what kind of flavor we want to make for this cheesecake, we will always follow this pattern knowledge. Another type of common knowledge we will touch base on in this tutorial is about the common sense knowledge. So we have a lot of common sense knowledge base. For example, we have the concept net, and then we try to inject this kind of knowledge to help the model to perform a lot of downstream tasks, like the vision common sense reasoning tasks. And to do this, we have 2 kinds of ways. The first way is whether we could inject the explicit knowledge about the patterns, and then we could manipulate the data set. We could add more supervision, and then we could also change the model architecture to add additional losses. Another way to inject this kind of knowledge is to use implicit knowledge sources. For example, we could learn from the massive data, try to discover this pattern, and then use parametric knowledge to help the common knowledge learning. For the last part of the tutorial, it's mainly about the model knowledge. So this is a new format of the knowledge, as we mentioned earlier. And this kind of knowledge will cover 3 types. So the first is the implicit knowledge that we can discover from language side. Especially now we have like GPT-based large language models, and there are a lot of recent research along this side. And then we also try to discover the explicit knowledge. So this kind of knowledge has the structures, and we want to improve the explainability and help the model to control why the knowledge can be used for these tasks. And another direction is whether we could use the vision side to help language. So this side we will talk about a lot of knowledge distillation tasks to see how vision can complement the language side. And in summary, when we talk about the knowledge-driven vision language learning, we basically can inject knowledge from 2 ways. So the first way is whether we could inject the knowledge for the model side. And another way is whether we could inject knowledge for the data set. And if we want to move forward for the model side, we can inject the knowledge by improving the compositional ability. For example, if we want to understand some abstract concept, maybe we do not need to annotate data, but we try to learn from existing concepts, trying to compose existing concepts together. And another thing is that we want to help the model to track long horizon context. So we can also help the model to formulate some new losses to enforce this kind of ability into the model side. And another thing is that when we have this knowledge injected into the model, whether we could locate where the knowledge is stored, and then we could edit this parametric knowledge. And on the data side, there are a lot of ways we can manipulate knowledge. For example, we could use the in-context prompt, we could use data augmentation, or we could use the knowledge to select better high quality data. So we also found that like data quality is much more important sometimes than data size. Another thing is that what is the effective feedback that we can add back to the model? So currently we only have like some up, some down, this kind of feedback. But the feedback is not really about this final prediction. We should also be able to add some feedback related to what kind of part is wrong, or whether there's some connection understanding or inference understanding is wrong. So this is more about whether we could effectively add this expandable feedback into the model. Then I'll start the first part about the factual knowledge capturing. Before that, we will also mention about the timeline. So firstly, we have this motivation session and introduction session. And after that, I will talk about factual knowledge and the common sense knowledge. And then Xudong will talk about procedural knowledge, and Jie will talk about the model knowledge. And in the last part, we will have a panel discussion to talk about some exciting questions related to whether we still need knowledge in the large-scale pre-training models, and whether we could borrow knowledge from like GPT-based model. Another thing is for different modalities, what's the bottleneck for each single modality? And if we want to bring them together, what's the bottleneck? So for the factual knowledge side, we mentioned earlier that we will focus on the 4 types of knowledge. So we have the entity level knowledge, relation level knowledge, event level knowledge, and affordance-based like physical world knowledge. So before we touch base on this single level of knowledge, we want to first broadly talk about why we want to move forward to this kind of multi-granularity understanding. For example, if we first check this image, we will have some impression about what is happening in the image. So as human, we will interpret the image as a woman is protesting with her children against the vaccine mandates. We can recognize this because we can recognize this visual pattern. So from the visual pattern, we can link the pattern of needle to the concept of vaccinations. And we can also link the pattern of crossmark to the concepts of negation. So this is how human can learn. And for machine side, we have a lot of tools. For example, we have object detection, and we have the singular passing. So we basically can figure out how the objects are connected. Like we can figure out the woman is holding the sun, and we can also figuring out their physical locations, like someone is behind the. If we map them to the language space, then we could map the object to the entity level information and map the relationships into the into the like knowledge graph, entity relation graph. But this kind of information is the entity-centric understanding. If we only rely on the entity-centric understanding, we can only get the interpretation like the woman is holding the sun. So if you remember what we human can do, we interpret as there's a protesting event, and their protesting goal is about vaccination mandates. So there's a large space between what we human can learn and what machines can learn. As a result, if we want to interpret the information behind the scene, we actually want to figure out what is the event here. So we want to figure out the event type, like it's a protest event. And after that, we want to figure out the participants, like there are parents and children involved. And for their semantic roles, they are the protesters in this event. Another thing is that there are a lot of banners, and these banners are the tools used in this protest event. As a result, we define this event extraction task for multimodal side because we want to borrow this terminology from the language, from the natural language processing side to reflect that there are complex semantic structures related. So for this kind of common structures, we can extract it from the images, videos, or other modalities like speech. And then we want to output the structure, like it can be a table, it can be a graph. And this structure will contain 2 parts. It contains what is happening, and also it will contain who are the participants. Especially we not only recognize who are the participants, but also want to recognize what are the semantic roles related to these participants. Compared to the entity-centric understanding, this kind of event understanding is not really about 2 objects. So it involves the multiple object connections. And the understanding is not just about some generic information, but we actually want to figure out what is the situation behind the scene. Like we do not want to only know this is a holding action, but we want to know there's a protest behind the motivation of the holding action. So we want to move from the entity-centric understanding to event-centric understanding to figure out how the activities and the event structures are presented in this image. As a result, our final goal is to move from this holding surface understanding to the deep understanding related to the motivation behind the holding action, like the protest event. And when we try to add the knowledge to reach this goal, we can bring this knowledge into the multimodal understanding by multiple granularity. So as we mentioned earlier, that if we want to understand that image, we basically can first read about like pixel level information, and then we try to focus on the objects and object labels. And after that, we want to figure out the scene graph. And then we also want to understand the situation knowledge, like event knowledge. And then we will try to figure out whether it's also can be grounded into the physical world. So our final goal is extracting the multimodal knowledge base, like given the image and the text side, we can construct a joint knowledge base that can connect the knowledge elements together from different modalities. And when we try to learn this multimodal space, we hope that the ideal space can embed any kind of structures or any kind of modalities into a joint space, like shown in the upper side. And then in this space, we have the connections between these like substructures, and the semantic similarity can reflect how they are connected. And then we could use this joint space to do a lot of tasks related to multimodalities. So in this tutorial, we will focus on how we can model each level of knowledge differently. So firstly, for pixel level, this is the most common like transformer structure. So we basically can use the patch level information to encode the pixels. And there's also model related to like pixel to sequence. So we want to convert the pixels into some sequence of tokens. So we could use language model based structure to model architecture to learn this pixel knowledge. And then the next level information is about the objects. So for the object detection part, we have a lot of existing models, like we could detect the objects, we could do segments, semantic segmentation, and we can also do like instance segmentation. And for the object detection models, there are like two-stage model or one-stage model. So I think these are some background knowledge related to object detection. So I will not include too much details here. And if we could extract the knowledge from like faster and this kind of pre-trained off-the-shelf model, then we could directly use these objects as the tokens. So here we could use the objects as part of the token sequence and input them into the transformer model and ask the transformer model to do the multimodal encoding. And this is another improvement, that we not only use this object bounding boxes, but we also want to use the labels here. For example, we have this object tag encoding. So this can actually serve as a bridge to connect the object bounding boxes and the semantics of the text set. So this model has achieved much better performance than the model we just showed earlier. But that kind of object information is some like off-the-shelf object detection results. So it's limited to some taxonomies. I think like for the open image, we only have 600 classes, but we actually have a lot of more classes in the open world. So we want to introduce soft prompt objects into the vision language pre-training. Basically, we do not detect the objects first. We try to get these bounding boxes and align them with the object labels. This kind of object label can be from any open vocabulary. So we call it soft prompt object labels. As a result, the model can firstly learn the stage of soft entity label prompting, and then it can use this kind of entity information to help with the final alignment. So this is how we can leverage the object information. And the good thing is that we have these object labels. So we can use this kind of label information to bridge the two modalities. And another domain is about the connections between these objects. For example, for the scene graph knowledge, we basically can figure out what are the objects involved in this image and what's the object attributes, and also whether these objects have any relationship between each other. So we have these three types of knowledge that we can use in the scene graph detection. And for the scene graph part, I think it's limited to the quality of the scene graph. So I only see one work related to this domain that we try to recognize the scene graph first from the image side. And then we can use this as a guidance to help the model to do the masking and to do the prediction. For example, if we can pass the scene graph as showing on the left side, then we could see there's some relationships, for example, on top of, and then we can mask these three tokens together. So this is about relationship masking. And then we could also mask the attributes information, like this blue kind of information is important. So I think the benefit from scene graph passing is that we could recognize what kind of tokens can be combined together to be interpreted into some semantics, like this relationship semantics and the attribute semantics. Another thing is that scene graph is also a tool to help model to figure out what is the important information. So it can bring up the information related to attributes and ask the model to focus on this attribute-based information optimization. And then on top of that, we also want to model the event knowledge. So compared to the scene graph knowledge, event knowledge is more about the situation. For example, the scene graph can be having long tail problems that a lot of relationships are about physical relationships, or it's about holding this kind of action. But for the event knowledge, we want to focus on more high-level situational understanding. So I think a lot of people ask me about what's the difference between this event knowledge and the scene graph. So that's the major difference of the granularity of semantics that we want to learn. And for the event knowledge, there's also a lot of explorations. So the representative work is situation recognition. Given one image, we want to recognize first what is a verb can be aligned to the image. And then we also want to generate a table to indicate what are the participants and what are their semantic roles. And on top of that, there are some extensions. For example, we can extend the situation recognition into a grounding task. So we not only want to know what are the objects involved in the image, but we also want to locate them into the image. And another thing is that we can extend them to video settings. So for each video of about 2 seconds, we can recognize them as some action. And then we can also recognize their participants and also build the connections between them. And another line of work is to do the extension on top of scene graphs. So scene graphs, we mentioned earlier that it has long tail problem, and most of the relationships are about some low-level semantics. So in this work, it's trying to build the connections based on scene graphs, but it's trying to extend the paired relationship into a multi-object event. For example, here, when we're trying to indicate this eating event, we can involve this girl, this cake, and also involve fox. So these are 3 objects involved in this event. So this kind of extension is more about whether we could change the paired object relationship into a graph that's related to multiple objects. But this kind of work all about the supervised training. So there's a bottleneck that we cannot handle open world events, and also we cannot scale up because we rely on this costly annotation. And another thing is this kind of work is about the vision only task. So it cannot align to the language side. As a result, we want to get rid of the annotation. So we try to introduce the supervision signal from language instead. And this kind of transfer is not a simple transfer, it's actually a structure transfer, because we want to understand how this table structure or graph structure can be reflected in the vision side. As a result, we firstly extract this structure from the language side. So we have a lot of tools from language side, like the information extraction tools, and we can use these off-the-shelf tools to extract the table here. we can recognize this is about the carrying event, and also we can recognize the agent is the protester, the target is the injured man, and the instrument is the stretcher. So we can use this table as the structure label for this image. But this table is just the positive label, and we also want to construct the negatives to help the model to distinguish this semantics. So when we construct the hard negatives, we can leverage like confusion matrix to select what is the most ambiguous event type. And also we could manipulate the structure of the participant part. So we can keep the objects as they are, but only manipulate the semantic role set. So this is the way that we can manipulate the text set, and then we can connect the structure into a natural language description using large pre-training models. So we use GPT-3 here to get the training labels for this image. And these training labels are related to the actions and the semantic roles of objects. And then we could use contrast learning framework to ask the model to distinguish this event semantics. So this is the first solution that we can leverage the linguistic clues to help the model to get the training data. And another part is we want to learn the alignment between multiple modalities. For example, from the text side, we could get a graph related to this event. So we have the triangle node to represent the event, and the circle node to represent the participants. And for the vision side, we construct the similar graph. We use the entire image to represent the predicate. So that's a triangle node. And then we use all the objects extracted to represent the participants. And our goal is to learn the alignment between these two graphs. So here the challenge is also we do not have annotation. We only know that this is about the image caption pair, so they can loosely align with each other. As a result, we can use optimal transport-based algorithm to align these two graphs. And this optimal transport algorithm will nicely enable us to use the unsupervised way to get the approximate solution between the alignment, approximate solution of the alignment between these two graphs. For example, we can leverage the sinkhole algorithm that we can define the distance between these two graphs and use sinkhole algorithm to optimize like 50 iterations using two variables jointly. And then we could get the approximate solution about the optimal transport plan. So this is leveraging the graph alignment algorithm to learn the unsupervised alignment between image and text graph. With this kind of solution, we could recognize any kind of event structures for the vision side. For example, given the image, we could try to align them with any kind of vocabulary. And from the vocabulary, we could rank the vaccination as the most close event. So we could detect this image as a vaccination event. And this is actually the first time that model is able to detect a vaccination event, because previously all the annotated data is like before pandemic. So this is not a type that we will focus on. So given this new scenario, this kind of unsupervised model is able to detect the new type of interest. And also the model is able to detect the structures. For example, it's able to detect the person in the middle is a detainee and the person surrounding him are the agents. And it's also able to distinguish the images with very similar visual features. For example, these visual features are about people gathering together, but the model is able to detect the first one is about protest event, and the second one is about celebration because of the objects involved and because of the like visual patterns, visual features. So this is the part that we could leverage the image information to understand the situation. And this situation understanding can be injected into the vision language pre-training models by manipulating the linguistic clues. And for the for the video side, maybe we could do the similar thing. We could understand the actions in the video. So for the action understanding, there are also multiple work recently coming up. So the first work is about whether we could understand the verbs. So it has a similar idea that whether we could manipulate the language set using linguistic clues. For example, we could manipulate the verbs here to a lot of different verbs and ask the model to distinguish these hard negatives. And another type of work is not just about verb understanding, but it's really about action knowledge understanding. So if we divide the action knowledge into 2 dimensions, it will contain one about the semantic understanding. For example, for the first task of action antonyms, if we have this video of the book is falling down, we could manipulate the action with the antonyms. For example, we could replace it with rising, replace falling with rising. And then we ask the model to distinguish the semantics of these 2 actions. And another dimension we could focus on is about the temporal dynamics. For example, given this original action text, we could manipulate the video side. We could reverse the video temporal order, and then ask the model to distinguish which video can be aligned to this text set. So the 2 probing tasks actually related to the 2 dimensions of action understanding. And then we also have a baseline task because a lot of models have received very good performance on these existing tasks. So we want to see whether it's really about the event understanding or it's really about the object understanding. So we have a baseline task related to object understanding. Basically, we replace the object with some object that does not exist in the image or video. So we can see the result is quite surprising. For the understanding related to actions like the blue bar and the orange bar, we can see the performance is very close to random. And for the object-centric understanding, that gray one, we can see the performance is close to 90%. So it shows that a lot of models currently, although achieve very good scores on the vision language pre-training benchmarks, but they are really taking a shortcut to use the object understanding ability to solve these tasks rather than really understand the actions. So we want to solve this problem. We want to patch the action knowledge into these frozen vision language models. So our goal is that we want to patch this kind of knowledge on top of the frozen model, and then we do not want the performance drop on this generic task. For example, we firstly patch the knowledge to generate some action-centric representation, and after that, we want to fuse the knowledge with the existing frozen visual language model so we can still perform good on some generic downstream tasks. And the first part is whether we could patch this knowledge together. So the supervision we can get is from the data set using like 2 manipulations. The first manipulation is about the action antonyms. So we could replace the action word with some antonyms. Like we could change the falling down to the rising up. And another manipulation is about the video set. So we could reverse the temporal order of the videos and force the model to learn the temporal dynamics. So through this kind of 2 manipulations, we could force the model to learn the action knowledge. And this part, we use the perceiver model architecture to learn this kind of knowledge. So this is the knowledge patcher that we learn, and it can generate the action-centric understanding. And we can see like with this kind of action understanding patcher, the performance boosts a lot on the action-based understanding. So we have this blue bar and orange bar showing how the action understanding is performing. And then for the green bar, for the gray bar, the performance is still very good. So it didn't drop the performance of the object understanding. And for the generic task, we actually also have a lot of tasks related to object-centric information, not just about the action understanding. So our goal is that when we add this patch to the existing model, we do not want to drop the performance of this generic task. As a result, for this action-centric vector that we learned, we fuse them together with some with the existing frozen video language vectors. So we use the cross attention to fuse the action vector and the original frozen model vector. And this will enable us to achieve very good performance on 3 kinds of tasks. So the first task is about the object-centric task. It can perform well, and then we can also perform well on the tasks that require joint understanding of objects and actions. And another kind of task is about like action-centric task that the model can still perform well. So this is the final goal of our model, to get this three kind of very good three kind of tasks improved. So if we want to validate the performance on the action-centric understanding, we will manipulate the data set. So firstly, if we have the original data set of the video text retrieval, we could like replace the object word to the common terminology like something. So it's kind of like we mask the object information and only ask the model to focus on the event-centric information to distinguish which one is the correct answer. And this actually shows that the model can perform well on all three aspects. So we just talked about the action understanding in the video, but action understanding also related to the participants. So this work is about the participant understanding by tracking the state changes. For example, if we want to understand the events in this video here, we basically want to focus on the object state changes. So here we have the object like this man. And the state changes can be related to two parts. The first part is about displacement. So the man, the bounding box is changing from close to far. And also another part is the pixel changes within the bounding box. So we can see the man is changing from this vertical position to the lying down position. As a result, we track the state changes for each object, and then we compose the state changes of each object together to figure out how the multiple objects are connected together. So this is how we could use a bottom-up strategy to transform the state changes of each object into the understanding of the events. And this finished the part of the event knowledge. And then the last part is whether we could ground the knowledge into physical world. So the first kind of knowledge is about affordance. So we actually want to leverage the like recent update in the embodied AI to help with this side. Basically, we want the model not only be able to see, and we also want the model to like talk, listen, act, and reason. So we want the model to do what the like language model generated rather than just follow the instruction. So here's the example. Like given the language model, we could predict the answer, like find the cleanser or trying the vacuum is the most close answer. But from the affordance side, because it's limited to the real world, so the answer can be like related to other aspects. And we actually need to combine them together. So we not only want to predict what is reasonable step next, but also want to predict what is actionable step in the real world. As a result, the motivation for this CCAM model is to ground the language model ground the language model output into the real world. And the model architecture is to learn a value function. So here we have the language model to rank all the candidate action steps. So this language model is not used for generation. So this language model is only used for ranking. And then for the value function on the embodied AI part, we also try to ground this part to the real environment to see whether that is actionable action. So we could combine these two parts together to get the final answer that is not only reasonable, but also actionable. And some interesting exploration in this work is that it also tries to incorporate chain of thought in this kind of planning task. So it not only just generates the like next step, but it actually tries to help the model to reason about why there's a next step. For example, for the first question that the human is asking whether a fruit flavored drink without caffeine can be brought. So the robot can know like it's about lemonade because it can reason about that this drink should be fruit flavored, and also this drink should not have caffeine. So it actually have this reasoning chain about what is the actual targets that the human is asking for. And another exploration is about whether language model can be grounded into the embodied AI signals. For example, we basically can extend the input into the multimodal input. Like the model not only take the text tokens, but also take the image tokens, and also can take other like format of the tokens. And then it generates the action labels for the model to like learn, given this multimodal input, what kind of action should be generated. So this model also show very good performance by incorporating the embodied AI signals. And another kind of model is trying to take the multimodal input, but also generates the multimodal output. So last model is about like language output, and this model is generating the real like signals in the embodied AI part. For example, the input side, it also has like multiple modalities. So for the orange nodes, it's the text tokens, and the purple nodes are the object tokens. And then it's trying to take all the different modalities together to generate the action labels that can be used in the real environment. And the training architecture is like this. So it basically have this multimodal prompt with the object encoder in the real world environment. And then it tries to generate the action grounded on this real world environment. So for this kind of model, we can also learn something for like future line of work in embodied AI with language models. So basically, this kind of success are achieved not only from this cross attention of different modalities, but also we want to involve a lot of object-centric information. So this actually reflects the conclusion that we mentioned earlier, that the current model benefit a lot from the object information. And I think this also represents like future direction, whether we could also move this line of research from object-centric information capturing to the action-centric information capturing. Because embodied AI, this kind of real environment is not only related to objects, but current model will highly rely on the object-centric information. And we actually, if we are able to inject the action knowledge into the embodied AI and language understanding, then I believe the performance will also boost in a lot of like tasks that require accurate planning. So going forward, the future challenges will also focus on these two parts. So the first part is whether we could learn the alignment between different modalities by understanding different granularity of semantics. So this related to the structures of how this granularity of semantics are connected. And then we also want to move to the higher granularity of semantics, like we want to understand the abstract concepts. So the first part, to understand the structure level alignment, we actually have a very, very complex structure in the vision side. For example, we have this graph structure, and we also have the detailed information from the vision side that can be captured. For example, when people are sitting on the sofa, it involves several state changes related to sofa and related to the physical relationships between the man and the sofa. So this is some detailed information that vision side can be captured, but language side, we will not do such detailed like description in natural language. And from the language side, it also has very good ability in terms of long distance planning, as we mentioned earlier. So we believe this kind of two modalities can be brought together using this structure level alignment. And another direction is that we want to understand the more higher level granularity of semantics. So we want to understand the abstract semantics and understand like how the semantic structures are connected. This is very important for this era of large-scale pre-training, because nowadays we have this like large language model. have a lot of bottlenecks related to the it's not open world knowledge, so it cannot keep updated with the real world knowledge, and also it didn't perform well on the long context reasoning. So this bottleneck basically reflects that it's understanding a lot more on the surface semantics, but for the deep semantics, we still need a lot of things to work on. By moving from surface to deep, we actually can be like concretely focus on these three parts. The first thing is we want to move from concrete concept understanding to abstract concept understanding. Another thing is from static to dynamic, and also from perception finally to cognition. And to achieve that, we need to extend this to bottlenecks, like extend the bounded knowledge to the compositional novel concept discovery. So we could discover new concept based on the historical concept that we have learned. And also for the short context capturing, we need to extend it to the long horizon understanding. So to move forward, there are a lot of different work trying to focus on multiple aspects. Firstly, for the abstract concept understanding. So this is actually about the abstract shape recognition. So even if this shape is not related to some real world objects, we human can still interpret it into some animals. So this is some ability that when human can recognize the abstract shape. And another thing is that we want to recognize the higher level granularity of semantics, like how we can teach the model to represent the image is related to love, happiness, this kind of emotional word. And another thing is from like audio speech side. I think audio is very good at representing emotions. So how we can include audio into this abstract concept understanding is also some interesting question. And another thing is about compositional understanding. So given this image, machines can recognize there are a lot of humans and they are sitting around the table, but we actually have a lot of information embedded in the image related to like social distance. So we want the model to know, like when the distributed pattern is like this, it actually related to the concepts of social distance, and the social distance related to the concepts of COVID-19. And also from the actions, like we can see some people wearing medical uniforms. So they are doing the injection action, and then this is about COVID-19 vaccination. So this is how we can ask the model to detect the little pieces of information and connect them together to compose to a very complex concept. And this kind of ability can also involve the logical relationship control. For example, if we want to compare the concept of cape and the cloak, their differences about like whether it's wearable by wizard or not. And another part is whether we could understand the underlying bias behind the language and behind the vision set. For example, for each video, different news agencies will put very different news titles. So they will reflect their ideology and their political stance. So this basically also related to misinformation detection in the multimodal setting. And we believe this kind of understanding will highly rely on the ability to understand abstract concepts, because we actually need to understand like what kind of emotion people want to trigger using the image. And one potential solution I'm very interested in is whether we could use language to help with this kind of multimodal abstract concept learning. For example, given the image, if we just input a lot of detailed visual observations, like there's a dog, there's a soldier, and there's a baby, and then ask the language model to output what is the situation behind it, the language model will be able to know like this is about people are doing the rescuing event. So language model has very good ability to compose the low level observations into the high level situation. So we believe this is some ability that we can borrow from language as well to understand the novel abstract concepts. And there are a lot of open questions related to evaluation, like what is the correct evaluation metric to show whether the performance gain is from the knowledge or it's just from more data. And also, we want to link the explainability and the reasoning to this like large language pre-training with knowledge. So this is actually something between symbolic neurosymbolic AI and also the large language model pre-training, large model pre-training. So we want to see how these two can be brought together. And another thing is that if we store this knowledge into the large models, whether we could edit the parameters. Also we have this bias in the learning process, especially I kind of feel when humans rely on this annotation, alignment annotation to learn multimodal foundation models, they basically will rely on how human represents the information. So the open world knowledge will include the bias. As a result, we can move forward the multimodal learning by injecting this factual level knowledge from not only entities relations, but also try to focus on the complex event structures and try to ground them to physical world knowledge. So I think we can take a 5-minute break. So this is the first hour. Yeah.
Zoom 里面说没有 slides， 然后要不我们现在就临时传一个。可以的。就是要不就比如说传一个。传一个。
你等一会儿传，我先我要先让我这个下一个CVPR。 Yeah, so let's start it. Yeah. And so this part is about the common sense knowledge in the vision language pre-training. And we just mentioned, like, for the common pattern knowledge, we will contain two parts. One part is about common sense knowledge. Another part is about like procedural knowledge and the external knowledge base. So for the common sense knowledge, we will touch base on three parts. Firstly, we will talk about what is the common sense knowledge that can be learned from multimodal side. And also we could see whether this kind of knowledge can be injected into the vision language modeling. And after that, we want to talk about whether we could distill such common sense knowledge from vision language pre-training models. The first part is about what kind of knowledge we want to discover as common sense knowledge in the multimodal side. So there are a lot of common sense knowledge benchmarks related to like visual common sense reasoning. For example, given the image, the model is trying to understand not only about what's objects in the image, but it's trying to understand why the person is doing this event, and then trying to give the rationale about why the person is functioning like that. And the extension, an extension about that is trying to add the temporal dynamics. So this kind of understanding now requires the model to understand what is happening in the image and what's the motivation behind these actions. But also you need to understand how these actions are connected, like like here we actually have three types of knowledge. So like the yellow box represents like before this image, what is the event, and the blue box represents like during the image, what's the person's goal, and then the green knowledge represents what's the event might be happening after the scene. So this is trying to understand the temporal reasoning alongside this like events within the image. And this requires to actually connect the events together using the common sense, like what kind of events can be before the current scene and then can be after the current scene. And another thing is that this kind of understanding has contributed to a very large data set that contains a lot of annotation related to this temporal reasoning. Another type of knowledge, common sense knowledge, that we can discover from multimodal models is a physical world knowledge. So for example, for the first sentence, for the first goal, like if we want to make an outdoor pillow, then we should not use the tin can, but we should use the trash bag. So this is something related to the task of performing, and we still feel like it's about the common sense reasoning. And this kind of knowledge can be discovered from the language model by asking appropriate questions. And there are a lot of data sets trying to focus on this kind of task related common sense knowledge reasoning. For example, something data set, and there's a lot of new data sets related to like Ego 4D. Like we also can use this kind of data set to help with the common sense knowledge related to this physical world. And another type of knowledge I think will be very interesting is the precondition knowledge. So for example, if we want to make the drum make noise, then we need to beat it. So these are the preconditions to make the event happen. And to learn this kind of knowledge, there's also a lot of models trying to distill such knowledge using like language model as some minimal supervision. So we just finished what kind of common sense knowledge we aim to learn from the multimodal pre-training models. And then we can talk about how we can inject such common sense knowledge to help with the learning. For example, current pre-training models cannot perform well on this common sense reasoning task. Like if we want to map the image with the sentence, this tastes sour, then clip and the flip and other models will all select the second image, and the score is kind of very high compared to the first image. But as human, we definitely know like bread or cake will not related to the terminology like sour. So we want the model to get this kind of common sense knowledge from the vision side. So we can augment this kind of knowledge from external knowledge bases. So basically, there's work trying to incorporate the knowledge graph into the learning process. For example, given the image, it's trying to link the knowledge elements into the knowledge graph. For example, we can link the cat to the like knowledge graph and then get some triples related to the cat. For example, the cat is a type of animal. And also for each different object, they can also get the triples like box and office. After that, it will try to merge the objects that related to a very close like physical location. For example, the cat and the box can be merged to this atom, and then they can merge their concept triples together. So the final goal is trying to generate the data that can interpret this original image into a lot of common sense knowledge triples to reflect the physical locations and also to reflect their attributes and properties. So this is some way that we could construct the data set and then inject this knowledge into the pre-training. And another way is that, and for the model side, we basically have two parts. The first thing is that we could retrieve the knowledge from the knowledge bases. This is the upper side. And for the bottom side, it's the model that we are trying to encode the knowledge graph with the image. So from the knowledge graph side, we could use like graph embedding, position embedding, type embedding to contribute to a joint embedding. And then we could aggregate it with the original like image embedding. So when we're trying to answer the question related to common sense reasoning, we could leverage the knowledge here. And this is some recent work that we are not only trying to bridge the knowledge graph into the pre-training, but we're also trying to help the model to understand a lot of common knowledge by prompting. So for example, to answer the first question, like explain why the photo is funny, it's trying to generate the explanation related to the cat is wearing the mask. And this mask has a smile symbol on it. So this kind of information is kind of like chain of thought. So it basically trying to give model more explanation and then help the model to reason about this common sense knowledge. And this kind of model has achieved a lot of success related to not only language tasks, but also cross-model transfer tasks and also like vision tasks and perception related tasks. The last part is about whether we could distill the knowledge from vision language pre-training models. So whether we could already generate a common sense knowledge base directly from the large models. For example, for the vision or physical world side, the knowledge we can focus on will contain three parts. The first part is about the spatial knowledge, and another part is about the size, and then it's about the color. So these are the common knowledge that people will discover from multimodal side. And when we're trying to discover this kind of knowledge, we will use prompt from the language side. For example, we just trying to construct the prompt for each type of the knowledge that we want to discover. And another thing is that when we're trying to discover this different knowledge aspects, we will also introduce a lot of different relationships or like inference relationships. So we will capture part-whole relationship, and also similarity, quality, temporal, spatial. So this kind of different aspects to trying to connect this common sense knowledge. As a result, the training architecture will be trying to ask the model to distinguish from the negative relationship triples from the positive relationship triples. So the final goal is trying to ask the model to recognize that mouse usually located in some like forest or other, but it will not exist in beach. So this kind of information is just trying to like use this kind of knowledge triple structure to help the model to learn the contrast learning. And for the spatial and the size and other kind of relationship, we have the similar data set. So we basically just trying to formulate this kind of relationships into triples and then ask the model to answer this kind of question. It's exactly the same architecture as this one. Some interesting discovery is that when we're trying to model visual common sense knowledge, it's actually much more difficult than the textual knowledge discovery. For example, if we check the scores, we could see like the performance. If we use like BERT and Robota, this kind of text-only model, it can get very high scores. And if we just use the vision model, a lot of times it didn't perform as well as text models. So this also shows that if we want to discover this common sense knowledge, maybe we could try to leverage the knowledge language side and trying to help the multimodal side. In terms of the modalities, we also check whether the common sense knowledge can be discovered differently for unimodal and multimodal. Like for the unimodal side, we have a lot of pre-training models, and then for the multimodal side, when we train the models, we basically are able to capture the common knowledge from the image as well. So if we compare the common sense knowledge related to color, shape, material, and other like size, this kind of physical common sense knowledge, we will compare them with using this kind of data set by asking the questions here. And then we could find that the abilities from like multi-modality common sense capturing is kind of like much more difficult or lower compared to the single modality common sense knowledge discovery. So I kind of feel this related to the future work, like when we're trying to capturing the common sense knowledge, what is a good way to actually bring different modalities together? And also this kind of common sense knowledge, we only have very good way to like retrieve knowledge or just trying to distill knowledge, but we didn't have a very good way to use this common sense knowledge to control the pre-training. So there are a lot of future direction related to this line of research. For example, for human side, if we want to answer this kind of question, like put the object A to the left of object B, and then do other kind of manipulation and ask the model to predict the final physical location, we basically can have this mental simulation about how the physical location will be changed after each moving event. But for machines, it do not have this kind of ability. So if we play with GPT-4, it will always generate the wrong answer. As a result, if we want to inject this kind of physical world knowledge into the pre-training, we can also focus on like action-based understanding first. We want the model to like not only do the action classification by comparing about starting frame and ending frame, but also trying to figure out what is the like future state changes after this action. And finally, we want the model to be able to answer this kind of question, like when we're trying to manipulate the location of the chairs, the model is able to have this mental simulation and trying to accurately understand like what is the location changes after each kind of action. And another direction I would like to share is whether we could incorporate this common sense reasoning ability into the task by disentangling perception part and the reasoning part. So there are also recent work related to like Viper GPT related to using this reasoning ability for the multimodal tasks. Like given the image, if we want to answer the question, what is the average number of muffins that each kid can get, we can write a code to firstly identify the image patches related to muffins and the kids, and then the code generation will give some formulas to like divide the number of the muffins by the number of kids. So this kind of reasoning task is also trying to leverage the ability from the language side. It's using code generation, but I cannot feel they are similar, just trying to use the language representation ability to help the reasoning part. So this is the first trial that we try to disentangle the reasoning ability with the perception ability. So the model can just use the perception ability as a tool, and then figure out how to leverage these tools to process the multimodal information. But this work only have very simple reasoning task, and it can only handle like single image, so it cannot incorporate long context understanding. But for the real world understanding, if we want to answer some questions related to reasoning tasks, then we actually need to jump from different information nodes. For example, if we retrieve the news articles related to the question like, at which festival can you see a castle in the background? Then we need to retrieve a lot of image related to festivals, related to castles, and then we need to bring them together to joint inference. So this actually is a much more complicated reasoning task. As a result, if we want to achieve this, we definitely need to separate the perception with reasoning ability. So we could use very good perception tools, and then we could do divide conquer to reason about very complicated questions. So this finishes the common sense knowledge part, and then let's welcome Sidong to introduce about the procedural knowledge.
Thank you, Melanie. And hello, everyone. My name is Sidong Lin. I'm currently a final year PhD candidate at Columbia University, and I will talk about methods about procedural knowledge. So in this part, we mainly talk about methods learning patterns of procedure with human-created patterns of procedure, or directly learning from massive data. So what is procedural knowledge? In psychology, there is actually this nice hierarchical categorization of knowledge. Based on whether the knowledge is a factual statement or not, there is propositional knowledge. For example, I know Ottawa is the capital of Canada. This is a factual statement about the real world, which is a typical case of propositional knowledge. And for non-propositional knowledge, there is knowledge by acquaintance, like I know someone. And finally, there is procedural knowledge. I know how to do something, which is the main part of my talk. And here we want to show a few machine learning tasks that require procedural knowledge. For example, procedural planning. Here, given a start image and an end image as the input, the model is required to generate a sequence of actions. And the sequence of action will gradually change the states of involved objects, which lead us to the final state presented in the final image. Another example is step forecasting, where the model is given a historical video, and the model is required to predict the next step, which clearly requires the model to understand the procedure of accomplishing certain tasks to make the correct prediction. Now let's talk about methods about procedural learning. Here we categorize existing methods based on whether the model has access to explicit knowledge source. So for the first category, the model will learn with the help of external knowledge. But what is explicit knowledge source we have? The good news is that procedural knowledge can be rather easily curated from the internet. For example, in this recipe 1 million data set, the authors curated millions of recipes from online web pages. And each web page contains the step-by-step cooking instructions and also ingredients and the example image of the dish. Another example is WikiHow, which covers a much more general domain compared to recipe 1 million. On WikiHow, if you just search for a task, you probably will find an article giving you detailed instruction of accomplishing the task. And on WikiHow, the articles are usually verified by human experts, which really makes it a good, high quality knowledge source from the internet. Now with all these possible knowledge sources, let's really go to the methods utilizing these knowledge sources. And when we talk about a general AI system or machine learning model, there are usually three key factors, right? What kind of data do we have? How do we supervise the model? And what is the model design? So let's first about the types that using knowledge source as data. One of the representative work along this line is zero-shot anticipation for instructional activities. And here the key idea is exactly to obtain training data from knowledge base. So in this work, the model follows a two-stage training process. In the first training stage, the model takes millions of sequence of steps from the recipe 1 million dataset. And in this training stage, the sentence encoder is trained to encode the step sentence into a step vector. And then the recipe network, which is formulated as an RNN, is responsible for modeling the procedures. And finally, the sentence decoder is trained to decode vector back to actual step sentences. And in the second training stage, only the video encoder is trained to project the video into the step vectors with manually annotated data, so that the knowledge learned by the recipe network will be able to generalize to scenarios with actual video as input. And finally, in downstream inference stage, with a video from an unseen task, hopefully the model will be able to generalize and generate next steps based on the historical video segment as input. In this work, they found empirically the model indeed achieves strong zero-shot performance on their proposed tasted video dataset. And it is also showing that the larger knowledge base used, the better downstream performance is achieved. However, this work is still rather limited. For example, the domain is limited to cooking because of the recipe 1 million dataset knowledge source used. And this second training stage in this work also relies on annotated dataset for training the video encoder, which definitely limits its generalization towards broader, unlimited, unlabeled video scenarios. And very recently, there is a following up work published on ACL this year that further extends the step sequence to non-sequential scripts. And the key idea in this work is that we can ground WikiHow steps to video observations. And in this way, we will be able to obtain the non-sequential scripts, because in actual video observations, it really contains a lot of real-world variance. For example, some steps might be skipped in the real-world video, and in some cases, the orders of two steps could be also possibly swapped. So with all this real-world variance, we can really obtain scripts in a non-sequential manner. And similarly, in this work, the model is also a next step prediction model. But since the sequence is obtained from real-world video instances, if we really let the step prediction model to decode sequences of steps, we will be able to obtain various different sequences for the same task. And if we just merge the multiple decoded sequences together, we will be able to really obtain a nice graph like this. However, in this work, it's also limited because of the vocabulary. Since in WikiHow, it's closed vocabulary, it's fixed set of tasks, fixed set of steps. And the graph here is also text only. As we can see, it's only text descriptions of the steps. We cannot really add possibly new steps from video observations into the step, into the graph, which is finally introduced here. And now we will talk about the second tab, where we try to leverage the external knowledge source as supervision. One of the representative work here is from CVPR last year, where the key idea is that we can try to leverage pre-trained language model to help us align the knowledge base and videos with speech to obtain supervision for training video representation. Specifically, first we need to construct a step knowledge base. And here we look at the 1,000 most popular tasks from a large-scale instructional video data set called Hot 100 Million. And then we try to find the corresponding articles on the WikiHow webpage and try to collect the sentences for each step in each of the tasks. And in the end, we collect 1,000 tasks and 10,000 steps, which is already one order of magnitude larger than the existing manually labeled data set. And to create the distant supervision, the key idea here is that we can leverage a pre-trained language model to measure the textual similarity between a step and the ASR sentence from an instructional video. As we can see here, the assigned step based on the textual similarity really has much higher textual quality compared to the ASR sentence, and the alignment between the visual frame and the assigned step is also pretty good. So overall, this work follows a two-stage training process, where in the first pre-training stage, we use the distant supervision to train video representation. And in the second stage, we can leverage the video representation and the order information in the knowledge base for downstream tasks. For example, if we want to do step forecasting, then we can first identify the current step in the input video segment. And then based on the order information in the knowledge base, we can find the next step and use this as an augmentation of the input to the downstream classifier for step forecasting. And overall, empirically, we found that the WikiHow knowledge indeed provides pretty high quality distant supervision, even compared to manually labeled data sets like kinetics, or compared to directly using ASR. But this work is also somewhat limited. For example, in the pre-training stage, we only leverage the step itself. We didn't really employ the ordering information. And very recently in the CVPR this year, there's a follow-up work further leverage the ordering information by constructing procedural knowledge graph and then use it to obtain supervision. So to obtain the procedural knowledge graph, the idea is actually quite similar to the concurrent work published on this ACL this year we covered earlier, where the key idea is similarly to obtain variance from actual video observations, and the actual video observation can provide us different sequences, and by merging the sequences, we can obtain graphs about certain tasks, And in the second stage, we really leverage the knowledge graph to provide a supervision. And here, 4 loss terms are proposed to comprehensively leverage in the knowledge graph. The video node matching loss in the basically enforce the model to recognize the step correctly. The video task matching loss enforce the model to recognize the task of the video correctly. And the task context learning loss enforces the model to recognize the relevant attributes about the video correctly. And finally, the no relation learning loss enforces the model to understand the temporal order of steps correctly. After training with all the 4 loss terms, the representation produced by the procedural aware model will be directly used for downstream tasks like task classification, step recognition, or step forecasting. However, in this work, it also shares similar limitation to the ACL work we covered earlier, where it is still closed vocabulary because of the WikiHow knowledge source used, and the knowledge graph here is also text only. The third type we would like to introduce here is to directly use knowledge as part of the model. Here, one representative work is induce, edit, retrieve from UPenn. The key idea here is that we try to learn multimodal schema script to represent the procedural knowledge. And here the algorithm follows a 2-stage process. In the first stage, we first try to induce schema for known tasks. So for each task, we can first try to find corresponding steps from WikiHow, and then try to find videos from YouTube. And then for each segment in each video, we can retrieve the most relevant step with existing video to text matching models. And then we have this sequence of steps. And for each of the steps, we also have associated video segments. We call this collection of both text and video segments as the schema for one task. And in the second stage, since in actual inference there could be unseen tasks, and in this work they try to propose a schema editing algorithm to generalize to unseen tasks. So first we will try to find the most similar seen task based on both textual similarity and the visual similarity, and then we will replace the key objects in the task name. And then we will try to delete some steps that are not really relevant to the new task based on a pre-trained language model. And then for the remaining steps, we may also need to replace some tokens to make sure it is really aligned with the new task we are dealing with. And this stage is also done by prompting a pre-trained language model. So overall, with the schema and the schema editing algorithm in this work, the authors show the effectiveness on the schema guided video retrieval task, where the model is given a task text query, and the model is required to retrieve a long video as output. But it is really difficult if we want to directly retrieve a long video based on the task text query, since there is no intermediate level of information. And here the schema helps because we can generate a schema if it is an unseen task, or maybe we can directly retrieve the task related steps from the schema if it is a seen task. And the retrieved steps or the generated steps will be really a good intermediate level information for us to retrieve long videos more accurately. However, in this work, it is still rather limited, since as we can see, the schema here is still restricted to step sequences, but it doesn't really consider the possible graph structure like optional steps or interchangeable steps. And the downstream task in this work is also rather limited. It's only text to video retrieval. So as a summary, in the three earlier works for each of the category, they are all focused on sequential knowledge, and only the induce edit retrieve work tackles the multi-modal part of the knowledge. But we also see recently this year, there are also following up work tackling the non-sequential knowledge. But we still want to ask, what is the next step for methods of using explicit knowledge source? And one future challenge I think that is important and interesting is about interpretation of the model and the knowledge. So currently, we don't really know whether our model understands why the steps are altered in the knowledge base. Right? The model may not really know the precondition relationship between cut lemon in half and squeeze lemon to get juice. The model may not really understand what is the intent of add sugar. To really let our model understand these reasons behind the knowledge structure, I imagine the model probably really needs to understand more about the physical world, and we probably need better interpretation methods and evaluation metric to understand how well our model understands it. And another open problem is on the open vocabulary side. Here by open vocabulary, I'm not only referring to generalization to new tasks. As we can see, this is also somewhat covered by existing methods. Although I'm not really saying existing methods can already handle the generalization, it could be definitely still improved. But more importantly, I think the possible discovery of new steps and for the name the new steps and added the new steps in the knowledge base with correct connection with the existing steps is still really a challenge that probably no one has really tackled. Okay, so now let's talk about methods using implicit knowledge source, which is to directly learning procedural knowledge from massive data. The first work we want to introduce here is MERLOT, where the key idea is to learn the temporal reasoning ability through massive video data. And in this work, there are three pre-training objectives to pre-train multimodal transformer network. The first two training objectives, the alignment loss between frame representation and text representation. And the second objective, mass token modeling. These two objectives are rather common vision language pre-training task objectives, since in the first one, it aligns the space between the visual representation and the text representation. And in the second one, it helps the model to at least extract the knowledge in the language part input. And here the key difference is the temporal ordering loss, which is formulated as a binary classification loss between pairs of frames as the input. Empirically, in this work, the model indeed shows strong temporal reasoning ability on downstream tasks like ordering images from visual stories or predict future events given historical videos on the VLab dataset. However, in this work, it is still rather limited to its short temporal span. In real life video, we probably see much longer than a few seconds. And the other part of limitation is that the importance of the temporal ordering loss is not that clear. It is also possible that the mask token modeling loss also captures certain temporal relationship from the language side. The follow-up work, Merlot Reserve, further add audio as an additional modality. And here the objectives is also unified to a contrastive loss design between the predicted representation of the masked audio and text and the actual representation when without masking. And with this additional modality and the unified model design, empirically, the authors find that there is indeed an improvement in terms of video understanding and the video language performance with the help of a module, with the help of audio. But in this work, it is actually rather limited since we are not really that sure about the procedural knowledge improvement, since it is not really evaluated on the two tasks used in Merlot earlier. And next, we want to talk about another work from the NLP side, which may possibly Yeah, really sorry about the technical issue. Let's resume our presentation here. So we just talked about the possibility, the alternative possibility of leverage large language model to obtain procedure knowledge. And this work is actually in the area of embodied AI, where the key idea shown in this work is that large language models indeed has learned rich procedure knowledge, and such knowledge can be actually extracted. So the key idea, the key focus of this work is actually more on how to prompt large language models to generate steps that are really executable for embodied agents. But from the view of procedure knowledge, if we look at the generated steps, they are already pretty good and sense making, and the sequence really seems to lead us to the accomplishment of the task. However, in this work, we still have a lot of challenges if we really want to adapt it to video-related tasks. The main problem is on the verification part. It is really hard if we want to verify on scale about the correctness of the generated sequence of steps, or the bias of the generated sequence of steps, or the groundability to actual real-world videos of the generated steps. So as a summary, for methods learning implicit procedural knowledge, there are also 3 key factors where we need temporally ordered data, and the pre-training objective should be also order aware, and the model should be also capable enough to really accommodate the reasoning ability along the temporal axis. For future challenge about this part, I think one important and exciting question is on the emergent abilities of large language models. So recently there are reports about after a certain skill, after a certain point of the model skill and the data skill, certain abilities of large language models suddenly emerge, like the accuracy suddenly improves. Although there is also recent argument on this, that this might not be really emergent abilities. It might be an issue of the evaluation metric, like the metric may not be smooth enough, which leads to this kind of sudden improvement of the final accuracy. But no matter what is the reason behind this kind of phenomena, it is still critical for us to understand whether we can learn procedural knowledge with a limited skill, which is indeed a practical problem for many, I guess for many research groups without that large scale resources. And another important challenge here is that existing training paradigm is really built upon temporally ordered data instance. For example, a video, which is essentially a sequence of temporally ordered frames, or maybe a text article, which follows certain order. But if you really think about real world complex tasks, like how to stop the spread of COVID, and if we really search it online, we probably will find a temporally ordered set of instances. And each instance could contain an article, an image, or maybe a video associated with it. But how to let the model extract the knowledge from this kind of temporally ordered sets, it's still an open problem. So as a summary format part, to learn procedural knowledge, model can either leverage explicit knowledge source, where it could be used as data, as supervision, or as part of the model. And if methods learn implicit knowledge directly from massive data, then we need temporally ordered data, temporal aware, objective, and capable models. We also identify interesting future challenges like interpretation of the knowledge, or the open vocabulary issue of procedural knowledge, or learning with limited skill, or maybe the shift from instance-based learning to step-based learning. So that's it for procedural knowledge. Now Jia will talk about the model knowledge.
the held-out datasets, we say that the instructional tuned model performs actually significantly better than the one trained with multitask. So instructional tuning is very important if we want to make the model more generalizable to different domain and tasks. So the method discussed above all require additional multimodal pre-training. Even though some of them require less compute than the others, it's still quite expensive for still a lot of people, especially people in academia, to train. Is there alternative ways to utilize knowledge in those large language models? And here are some like explorations in that direction. So the core idea is by summarizing the text information, summarize the image information in a textual format so that the language models could understand. Since the information are all converted into text, there is no extra training needed in this process. And this specific paper tries to solve the VQA task, the image QA task by converting the image information using an offline image to text model, which, for example, is an image captioning model. And with those provided image provided text context, the large language model could be able to answer a lot of questions. And we see here, actually in this VQA dataset, this paradigm actually shows much better performance than a lot of previous approaches which use explicit knowledge resources such as Wikipedia, showing the potential of this approach. And there's also one core issue with this paradigm, that the image to text models, they are not perfect. It will cause a lot of information loss when we try to convert the image into like a textual format. For example, the left example, the question is what color is a man's jacket? And the provided context is a man flying through the air while riding a snowboard. So as we can see here, there is nothing related to color in the context. So the model has no access or no way to get to the correct answer. So it's blindly answer it with a blank. So that's kind of showing what the information loss come from and how it will fail our model. And a similar idea has also been explored in the video domain, where the video information has been converted into text format in a lot of different levels, like object level, event level, or the frame level in the form of image captions. And those pieces of information are all glued together using some predefined formats. And those provided contexts are similarly forwarded into the language model to get to the final answer. And the Socratic model, which is more later work, creates more general framework for composing those different signals using large language models. And the core idea here is to use language as the general interface to bridge different modalities, like the vision language models and the audio language models. They all convert the original information into the textual format. For example, it has the visual language model converts the video of like a staircase into a textual format, the staircase. And then all those information are forwarded into the large language model to generate the final summary in this case. And it also has a lot of other applications, such as doing like generate pass and generate robot instructions. But this format actually has a very like big limitations that whenever we add a new model, we have to define how this new module would be used in this process, which means that human defines when and where to use which model. So this is quite a problem if we have a lot of different models we want to use. And what we define and the way we define when and where to use those models may not be perfect. So there is a more like a recent, like actually 3 months ago, after the more powerful language models like ChatGPT and others being introduced, there have been work tries to utilize those more powerful large language models to create new systems that automatically piece all the other APIs or other vision foundation models together to finish a task. And here in the Visual ChatGPT paper, what is the authors do actually is simply by defining the system where it's a visual chatbot knowing about like the visual information, and it also can manipulate image, and also it defines the name and the usage of vision models. It only defines like the name and usage, but not when and where those models should be used. And all those plans are completely made by the ChatGPT model itself without the intervention of human. And there's also another like similar direction. Instead of using natural language to control the plans, we also have a lot of language models that can generate Python code or other programming language code. So we can directly use those programming language to control, to compose the APIs to complete your task. So the Viper GPT paper is actually using the Codex model from OpenAI to composing different APIs to manipulate images. And more broadly, there has been a lot of work in the community that use ChatGPT and or like GPT-4 or the BARD model to accomplish various tasks, from booking a flight ticket to ordering food, or with like the GPT model to control the use of the tools and or APIs. So this actually is very has a lot of usages in many different scenarios. So so far we have been talking about large language models for zero shot multimodal learning. There has it shows some pros, like it is very efficient to utilize different foundation models across different modalities, and no extra training is needed. And the approaches are quite modular. We can simply update individual components without retraining the whole framework, or we can very easily plug into new functionalities into the framework to extend this ability. But as we discussed, it also has a big issue of information loss when we try to bridge those different models. And so far we have been talking about implicit knowledge, but those implicit knowledge from large language models, they're hard to interpret. Is there a more interpretable way that we can use language knowledge? And here we come to the second subsection, explicit knowledge from language. So here is the first work which tries to utilize the language from external knowledge base such as WordNet and Wikipedia to help vision task. And in this case, they started the image classification task and object detection task. And the way that they use those external knowledge base is actually quite simple. So they try to find a definition of some real concepts in the dictionaries and add that definition into the training process and also the inference process. For example, if we simply have the word sashimi, we may not have like a good chance of knowing what it looks like. But with the additional definition that it is a dish consisting of thin slices or pieces of raw fish or meat, we have better chance of recognizing it if we have no knowledge of what sashimi is. And with such like a simple method, actually achieve pretty good results. Let's look at the orange bar, which shows the relative improvements over previous models across different datasets. And we see that out of 20 image classification tasks, the model actually outperformed previous methods in 16 out of them. And in the ablation study, they show the most improvement actually comes from the datasets that with a lot of real concepts, which also aligns with our intuition. And in the follow-up work from same authors, they also tried to use the GPT-3 generated knowledge to define the category names, which is more flexible and has much higher coverage than human curated knowledge bases. And in the comparison on the right, we see that the model generated knowledge actually helps improve the knowledge which only sourced from Wikipedia. So showing that those two knowledge sources are actually complementary. So far, we have been primarily talking about how we can utilize language to help vision or vision language systems. We haven't been touched another direction, which is quite crucial, is how we can utilize vision to help language. And first, we start with this motivation that from a human perspective, visual point is actually an essential step for most children to learn about the meaning of words. For example, we point to like the cat and saying, look, this is a cat. So we can connect the textual concept cat with the visual presence of a cat. So we can build a connection. And this essentially helps us to better learn the meaning of that word. So we expect the similar observations can also present in the process of we learn language. We use models to learn languages. And here is the first work, vocalization, which tries to improve the language model by using extra vision supervision. And here the idea is still quite straightforward. Beyond simply using the standard mask language modeling laws, the language model is also trained with a Vulkan classification task by assigning each text tokens into one of the images, which they call Vulkans in the pool. And the Vulkans they use it for classification is predefined and is obtained by using an image text retrieval model. And with this additional vision supervision, the language model actually shows better performance on different, like on a set of tasks. And we say that this approach actually works for both BERT and the robot. The vocalization, although it achieved some initial success, it suffers from some difficulties. For example, the approximation error from utilizing or approximate finite image labels. And also it lacks the vocabulary diversity because they use only like 10K of image text data sets. This new work, the video language knowledge translation, where they improve the previous work by two different aspects. The first is using knowledge distillation instead of discrete vocalization to avoid such approximation error by using finite image labels. And the second, they use like larger scale video language datasets for training, which improves upon previous work with larger vocabulary. And the training is actually also very straightforward. There are two-stage training. The first stage is the cross-model pre-training, where they try to distill some knowledge, learn some knowledge from multimodal datasets into the teacher language model. And in the second stage, they perform a knowledge distillation from the multimodal teacher language model to the pure text student model in order to improve its performance. The teacher language model is trained with two different tasks. The first is the video language triplet loss, which tries to align the text and the language modality, the text and the vision modality. And the second is the standard mask language modeling loss. And for the student language model, beyond the mask language modeling loss, the knowledge distillation loss is used to distill the knowledge from the multimodal teacher language model into the student model. And here are some quantitative results. And we see the top table, which shows this approach actually works better than the previous vocalization approach because it improves upon like the affinity image label approximation error and also much larger vocabulary. And in the ablation study, the authors discovered that this paradigm using video language corpus to improve language understanding ability is mostly the gain is mostly come from like the three different subsets of the language. First is knowledge and the physical interaction and also temporal reasoning, because those are actually like exist more in the video language datasets rather than in the textual corpus. And here are some future work for like the whole like this subsection of the talk. And the first is how to better bridge language model and other modalities. And currently, as we say, like most of those standard work, actually, they all use frozen language models. So is this really like the final solution? Can we fine-tune it to get better performance? But the current community signal is that fine-tuning large language model actually hurts the model performance. But that could not be the final answer, because we have seen in other research directions that fine-tuning sometimes not work well is simply because we are either not doing it right, like not using the correct architecture, or we are not training it with enough data. And the second is, since like most of the work, they focus only on incorporating the vision modality, but there are a lot of other modalities surrounding us, like the audio and other signals. If there are more one modalities, extra modalities are needed, how to better model them together is still like an open research problem. And the second future work is related to like the vision supervision to language side. And right now, like the only exploration has been done is only on the bidirectional language model like BERT, but the causal language model is not explored at all. And also only very small model up to 100 million BERT model is studied. But right now we all focus on those very large scale models with over 100 billion parameters. Where the vision supervision could help language models still holds when we scale up the language model is still a question. And besides that, since we only studied the vision modality as supervision, can we use other modality as supervision as well, such as audio? That's still like a new frontier that has been explored. So the takeaway from this whole talk is, first, we have the we could use implicit knowledge from language models to help learn better vision or vision language models, such as we can, like the key idea is training vision model with frozen language model. And the second is convert multi-model task as text task for language model as input. And also there's like a direction where use explicit knowledge, either from human curated knowledge or from the generated knowledge from large language models. And another direction that we show vocalization or destination could use vision supervision to help learn better language models. And then also like the last part of future work, there are challenges that we are still facing is how can we better like bridge different modalities? How can we learn from more than like two modalities beyond just vision and text? And also there's like the direction when we scale up the language model, could vision supervision still be beneficial? So that's the end of my talk. Thanks. So in the next section, I think we will have a panel discussion about a lot of different questions and challenges that we are facing in today's world.
Hi, Mohit, can you hear us?
Did you open the speaker?
Yeah.
Did you need to find the file or what is?
I think it's okay. Yes, so
Otherwise, yeah, it's what is you can hear the audience can hear it. Right?
hi, Mohit, can you hear us? Okay,
Can you try saying something? We can test the sound.
yeah.
Oh, you're in
Oh,
mute. Oh,
I see.
host needs to unmute. Oh.
Okay, great. Yeah, I was trying
Oh,
to.
I see.
Yeah, I think there's some permission issue. Yeah, now you can hear me, right?
Yeah.
Yeah, good.
Good to see you.
We want to say and say more.
There you go. And then
Yeah.
so maybe we can make Mohit large. Let's see. Is there a way?
Bring you stand as well. Yeah, sure. Thank you.
There we
That's
go.
right.
That's better.
Yeah,
Now people can see him.
yeah, that's nice. Yeah. So,
Yeah.
thank you very much for attending this session. We are very excited to have this panel discussion about knowledge versus large models. So we are all very concerned recent days, especially now we have very strong foundation models, and we are wondering whether we still need this kind of knowledge and whether we still need to discover like explicit knowledge. And for the knowledge stored in the large models, whether we could find any like effective way to use that. So I'm very excited to discuss these kind of questions, and we are very fortunate to have our panelists to discuss these questions today together with us. And let me first introduce the panelists. So the first panelist is Carl from Columbia University. And he has worked a lot on the training models to interact with the surroundings, especially a lot of like robust models for perception. So it's also closely related to what we talk about, like we want to disentangle perception and reasoning. And also we include a lot of work from Carl's group in this tutorial as well, like Webber GPT and other works. So I'm very excited to have Carl to be our panelist. Yeah. And the second panelist is Mohit. I hope that you can see him there. Hi, Mohit. Yes, so Mohit is a pioneer working on the multimodal domain, and he has published a lot of well-known papers related to multimodal pre-training, and also he has done a lot of work trying to transferring the merits of natural language processing to the computer vision community, and vice versa, also transferring the advantage from the vision world to help with the language learning. So we are very excited to hear the unique insights of this question related to these questions from Mohit today as well. Yeah, thank you, Mohit. And also we will have Xudong and Jie to share their insights related to these questions. So the first question we want to touch base on is about whether we should explicitly represent knowledge or we can directly leverage the implicit knowledge inside the model. So I'm wondering whether, Carl, you have any insights about this?
Sure. Yeah, I love the large language models as a knowledge representation. And I really think we should just keep, I think it's a really great direction, just continue to use the implicit representation here. The problem with explicit representations is it's really hard to annotate and label. I mean, I don't know how many of us have sit in endless meetings that go on and on and on discussing like what the structure of the knowledge base should be. It's really hard to get that right. And so I think learning it is a really great way. There's obviously problems with the learning it still have to be overcome in terms of like bias and hallucination and all these, you know, well discussed problems. But I think using these large language models as a knowledge source is really great. And moreover, like the same language models that you know, are able to do natural language, they also work on code, right, which you can use as a way to query things, right? That's a good way of building structured knowledge bases, right? You can think about code as some sort of structure that encodes knowledge. So I don't think these have to be at odds with each other. Like I think you kind of, I really think this symbolic era, this neurosymbolic era is going to be riding on top of these massive language models, either through natural language or through code.
Yeah, so I think it's very exciting to know, like you also feel like symbolic knowledge can be integrated into foundation models to like learn about this knowledge. Yeah, I also feel like it's very exciting to explore this direction because it's kind of a like debate whether we still need symbolic knowledge. So I think maybe the final representation can be in the middle of them, like it's not really symbolic or it's not just only the foundation model, but maybe we should find something in the middle, find some sweet spot. Yeah. Xudong, do you have any insights about that?
Thank you. So I actually also agree that large language models are so powerful nowadays. But I do want to mention another part that may not be doable with large language models. For example, knowledge could be updated. Like maybe, for example, things are just changing, right? The world is changing so fast. But currently it is still not that easy to upgrade a large language model towards some new knowledge coming nowadays. And I think if we can somehow combine large language models with this kind of explicit knowledge source where we can verify and update frequently, that it's probably easier for us to keep up to date for the knowledge part of the system.
Yeah. Also, I kind of feel this updating is not just trying to add knowledge into the model, but it's also like related to whether we could locate them into some parameters, and when we revise these parameters, whether we could make sure we only affect the knowledge that we want to revise and keep the other parts exactly the same and as accurate as earlier. Yeah, that's very I think promising direction that we should work on. And also, Mohit, I'm wondering whether you want to share something.
He's muted. Participants.
Okay, yeah, somehow it keeps muting me. Maybe Carl, later you can make me a co-host. But yeah, thanks for the question. I agree with both what Carl and Xudong said. I think, I mean, it's a very hard question, right? I mean, there's a lot of debate on should we have explicit sort of knowledge being fed into models versus let these larger and larger models just learn everything. Oh, can you hear me?
Yeah, go ahead.
Oh, sorry. Yeah. So then, yeah. So I mean, it's almost like a very well-known debate at this point, right? That should we explicitly feed in knowledge versus learn this implicitly from tons of data being thrown into these models. I think a mix is good, right? There will always be some kind of knowledge, first of all, that may not be present in the kind of data we are feeding to the language models, or even if we have multiple modalities, right? Some implicit, unwritten, unsaid, unvisualized knowledge could be more explicitly fed in. Also, there's a lot of noise in the data being thrown into these models. So if we have some sort of precision and recall kind of trade-off, right? I mean, if there is some very important knowledge that you would really have to make sure is correct, then maybe explicit knowledge graphs is a better way to do that, right? Than hoping that the language model with noisy data is safe enough. So yeah, so there's a safety issue there. And also like the sort of, I mean, there's a data efficiency angle too, right? I mean, would you have thousands and thousands of examples and hope that the model learns that one fact, versus if it's really important to you to have the model learn that fact, maybe just give it to it explicitly. So I think it's in summary, to me, it's like a precision recall kind of trade-off, and maybe the more important sort of safety-based information, trustworthiness related information should be more explicit than relying on the model.
Yeah, it's very comprehensive answer. Yeah, I totally agree that how to find the balance between like precision and recall, and also like for the knowledge side, there are a lot of knowledge that didn't exist in the current modality, and we do need to see like whether we could also acquire knowledge that are not just in text or vision, and also when we're trying to learn the knowledge, or whether we could balance the like accuracy and also recall is like one important question, and also the safety issue of the knowledge learning. I think they are all like very promising research directions. And for this like explicit and implicit knowledge, I'm very excited to see like we have this kind of different opinions, and basically I think we not only need explicit knowledge, but also need implicit knowledge, but they both have a lot of remaining problems to solve. And for the explicit knowledge, we do need to see whether we want to leverage symbolic-based reasoning methods here. And for the implicit knowledge, we have a lot of problem in interpretation, in controlling the knowledge. So I think it's very like popular area, like how we could integrate them together rather than just choose one of them. Yeah, and next question I think is also very related. Sorry. Yeah, so the next question is about whether we could borrow the ability from large language models to help with the multimodality learning, because the large language model recently has shown very strong power, and it's kind of a trending topic, like whether we could transfer this ability from language to the vision space, or whether we could bring the best of two worlds together. So maybe this time we can start from Mohit. So would you like to share something?
Hello, can you hear me?
Yeah.
Okay. Yeah, I'll just stay unmuted, I guess, because every time I mute, then it makes me stuck. So yeah, so another great question. Thanks, Manling. So yeah, I think we saw some of this in the tutorial slides. You all did a great job there. I mean, one example, when I joined, Jay was presenting our Vidlan KD paper, for example, right, where I mean, it's the other way around, right? Where videos and other modalities, what can they what can language models borrow from them? But in this questions could be thought of as the inverted direction. What can we borrow from large language models? So one option, as I was saying, is that you could basically try to have a balance where the large language model, let's assume, has already tons of noisy data that's fed into it. So maybe if you have a trust issue you could force the language model to tell you what knowledge it has learned, right? So there's a lot of new work in this direction on where and what knowledge is stored in language models and how to edit this knowledge, connecting to Shudong's point about continual learning and how do we sort of make sure that this knowledge is getting updated regularly. So that's something that we could ask our language models, right, to make sure that they are telling us what knowledge they've learned. So that's a good way to do it, right? Because then you can check the knowledge first, if it's correct or incorrect, but you could also edit it, you could extend it, you could add the missing knowledge that cannot be learned from unlabeled, unsupervised data. So I think there's a lot of useful work from the community already in this direction, right? Distilling knowledge from language models into symbolic knowledge. Carl and I, like we've done work on programs, right? So we did things for and this is also a pretty old topic, right? Like all the way from when neural modular networks were introduced by Andreas et al. And then we did summarization programs, so language generation, then visual programming, Viper GPT, a lot of work has been doing, right? Like we did it recently for image generation, like can we do program-based? So this is another angle of the same thing, that can language models be first forced to tell you in neurosymbolic ways, right? Structured knowledge, can they convert their knowledge into more structure? But then the interesting new angles could be, can we check that knowledge, correct it, and extend it, right? So that to me is one good example of a balance between explicit knowledge and implicit knowledge.
Yeah, I totally agree that this kind of knowledge supervision can be introduced from the language side, especially it can give a lot of unique signal related to like symbolic reasoning, summarization, and also as you mentioned earlier, like there are also programming language, and the programming language is I kind of feel a better formulation. So I think this kind of research direction is trying to see whether we could use like this kind of knowledge to distill some important signal from large language model, and then to help the vision side. And there are a lot of like remaining tasks that we should tackle. Yeah. And also, Carl, would you like to also share?
Sure, I guess I can say I was originally I was skeptical of large language models and what that they learned. There's a lot of examples that you can come up with where it shouldn't work, right? It's like people talk about a 4-leaf clover more online, even though that's the rare one. So you think all these language models would learn, things that are more commonly discussed than what the reality is, right? It's not grounded in the physical world. But that said, like it's incredible what they do learn about like the visual world, the visual knowledge they have. Like GPT-3, which doesn't have images, right? It knows tons about what's going on in vision and about videos and everything. And I guess it's just because it's been trained from people who do have eyes, right? It's imitating what people do see. So, I mean, I think we see a lot of discussion at CVPR, especially about like what the role of language is in vision, right? And like clearly, if you look at biological vision, language has no role in that, right? Like we evolved vision first, you didn't, right? But it does seem like that, with these large language models, like they are able to actually replicate better how like your perception system might work, kind of in terms of more explainable, right? Because it's learning directly from you. It's learning from people about how to see. And so, in some ways, it's this is kind of a big contradiction to me, which I find surprising. Is like, it's biologically not plausible to learn from large language models, yet they seem to be more consistent with how a person would talk about an image, just because it's imitation, right? It's imitating how you process an image. So, anyways, this is some contradiction I often think about.
Yeah, it's very sharing about like how much we could trust the large language models. So like for myself, when I first start from this area, at that time there's not like well-trained large language models. So we try to think about like whether language can be benefited by adding the visual signals, or we can do another direction and introduce language signals to the vision side. And we also feel like during the experiments, we kind of feel the first direction, like when we're trying to add the visual signal to the language side, we get a lot of difficulties. And then when we're trying to add the language signal to the visual side, it's more about like how we could select the reliable part. I feel it's very exciting to hear Carl's thought about like when we leverage large language models, it's very important for us to make sure the part we borrowed is something that we can trust. Yeah, that's a very good point. Jie, would you like to share?
Yeah, I think Carol, Manny, and Mohedor talk about like the importance or the ability that language models could like accurate knowledge from external knowledge and basis or from human languages. I think there's one thing that I'm particularly interested in is like the ability for those language models to do reasoning. For example, like the ability for those language models to actually understand the human instruction and make plans to achieve a certain goal. And in achieving that goal, the language model is able to composing and different APIs or different modalities, like the models made for different modalities to achieve a certain goal. For example, it can perceive the physical world by leveraging like image or video foundation models. So that's kind of like a very like important directions to further explore. And there are also a lot of people, they are talking about like in the future personal computers, there might be two operating systems. The first is what we use today, the Mac OS or the Windows. And another is the language models, where the traditional operation systems, they handle with hardwares and other resources, or the large language models, they handle the interaction with human. So that's kind of what I saw the opportunity using large language models for multiple modalities.
Yeah, I think it's also a very good point about like the reasoning ability that we could borrow from language side. It's just when we are trying to like compose new concepts or trying to reach the goal, language side, it has this kind of planning ability or the ability to capture long context to understand how the little pieces will be connected and then composed together. And another thing I feel is very interesting that there like can be two systems in the future. Like for the language models, it can be some foundation model, and then we can use the perception or other vision models as a tool. So we could ask the language model to call like other tools to just perform all kinds of tasks. I think that's also some new paradigm to leverage large language models recently. So for the next question. The next question is really about different modalities. So I kind of feel currently we did a lot of research on the text side, on the image side, or on the video side. But like for the speech side, we still need to work more on it. And there's also other modalities, like recently there are a lot of work trying to connect the NLP with robotics, so we can get the embodied AI knowledge. And I believe like there are other domains like sensor data. So when we have this smart home, we can collect a lot of sensor data. And this kind of data modality is also rich in like some on-the-board data. So whether we could leverage these different data modalities. And I kind of feel for this multimodal research, it's really like trying to figure out two questions. One thing is whether we could model single modality better. And another thing is when we do not have a lot of annotation, whether we could align different modalities together. So, but yeah, so this time maybe we can start from Carl again.
Sure.
Yeah.
Yeah, and also I think it'd be good to get questions from the audience too. This would be great if people have questions to ask. Maybe it'll be controversial, and I think the bottleneck is the vision. I think that's the problem. And in a lot of these models, when you look at them, kind of the language and the reasoning is actually pretty good, right? Like with the code generation, like it can add numbers, it can do logical inferences really, really well. That works quite well. A lot of the issues, I think, with a lot of these systems often come down to the vision parts, where it's hard to still recognize objects. It's hard to track objects, recognize affordance, right? These like core vision tasks are often the hard part. So, you know, there's a lot of there's a great book called Mind in Motion from Barbara Tversky, who's also at Columbia. She's in psychology and studies. Her whole career was about studying studying the mind, right? And she makes this, her whole thesis is that a lot of your thinking is done spatially, right? You think spatially, you use your hands and everything. You're making spatial analogies for all of your thinking. And I think that that's like what we should be trying to build is these reasoning systems that have that type of reasoning, and that's a visual task, right? These are all visual things. But I'm curious what Mohit says, coming more. And Mohit, you're in both. You know, I grew up in the vision field. You kind of grew up in both fields. So I'm curious. Yeah, I'm curious what you think.
Yeah, I was very. I was smiling at your answer. Yeah, that's a good point. I mean, but I would also argue that that the counting and sort of the logical reasoning stuff is still a long way to go, even on the planning side and the language modeling side. So if we answer the first question about single modalities, I think we all probably know what each modality is good at versus not good at, right? Even first for humans, right? Before we go into models, or even in terms of data, right? We know that some facts are just not written down, right? They're more visual. Some facts are more common sense. They're neither visually in images nor maybe in written down in text. Right, audio has its own role, but none of these, right? I mean, combined will still be able to cover a lot of the interactive elements, right? So a lot of how humans learn is through action, reaction, right? Touching something hot, getting burned, then like remembering not to do that again. Hopefully, right? I mean, after maybe a couple of times at least. So these kinds of modalities, first of all, are still like we still need a lot more of, right? We cannot finish all of this research with multimodal large language models with just vision, like images, videos, and text and audio. So that's sort of one maybe direction to think about. And then in terms of bringing multiple modalities together, that's another big issue, right? A lot of these modalities don't talk to each other, don't align well. So there's a lot of, I think, related to what Carl was also saying, not just pure vision tasks having a long way to go in some subtasks, but same thing for also alignment, right? Between modalities is a big challenge. So for example, video and subtitles have always been a good example of noisy, misaligned, missing information. And then if you want to also have, you cannot rely on having data for all kinds of combinations of modalities being present as supervision, right? So how to deal with missing supervision for a lot of these combinations, but being able to deal with new combinations of modalities. So yeah, so I feel like both the single modality issue, right, that each modality is good for only certain things, which is why we need combinations. But even all of them currently combined, we are still missing a lot of modalities. And the second thing is the techniques involved in the combination, right, are also a big future challenge. We still have a lot to explore in how to be able to take, how to be able to merge modalities with a lot of missing information, a lot of missing data, right? Because as humans, we can do that a lot, but our models are still relying a lot on very explicit supervision.
Yeah, I think it's very inspiring sharing about whether we could connect that different modalities, although like for each modality, they have a lot of unlabeled data, and this like unlabeled data is also a very good resource, but we didn't have very good way to leverage them. I actually also have a question like related to this part. So I feel like for video pre-training, it's kind of lagging behind image pre-training, and also for other modalities like audio, this modalities is also like lagging behind. So like what could you also share something about like what is missing in the video, this kind of pre-training and also like maybe audio pre-training?
Yeah, actually, I'm thinking about the learning environment. Like if we also following Carl's points earlier on the biological side, like if we think about how human or even like general animals, creatures, how they learn to align different modality from their different sensors, they are actually learning from an interactive environment rather than a single task. And especially for video and audio, it's like, if we talk about real life, it's really an ongoing thing, right? We are constantly receiving the signals from the environment. So I'm just wondering whether it is possible that currently, when we break down the real learning environment into specific machine learning tasks like alignment between audio and video, alignment between audio and text, or maybe even simpler object detection, audio classification, when we break down the interactive learning environment into these specific machine learning tasks, are we oversimplifying the environment? Maybe we really need a more complex task to really enable the model to learn better from all the modalities together, I guess.
I guess in video, I think one thing that's missing a lot, well, Takeo Kanade, I'll quote him, is he's famous for saying there's 3 problems in computer vision. There's correspondence, and there's correspondent. And I think it's like true in video is like, that's really the key thing that's missing, what makes video so hard is finding all of the correspondences. I guess often corresponds as a tracking task, right? And I think this is why we haven't been able to leverage video as much. Like most computer vision systems, work on images, and that's been really successful, right? But video always lags behind, I think, because we just can't find the correspondences. We can't. That's the value of it, right? You want to learn physics, learn about human behavior from video. It's all about the motion and the dynamics, right? And to actually leverage that and extract knowledge from that, you need to be able to do these long-term correspondences, which just as a low-level visual processing task just hasn't worked as well. We have systems that can track pedestrians. That works well, but it's still very short term, right? When there's occlusions, it doesn't work, right? And so I think this is really a key bottleneck here.
Yeah, especially this correspondence is kind of I think some bottleneck in the video understanding. I totally agree. So previously I thought for the video side, there's no very clean like alignment for videos. So we have this like instructional videos that compared to image captions, I cannot feel instruction videos or other video resources. Their text alignment is not very good because like different people will have different interpretations even for the same video, and they will cover like multiple granularity of semantics. So I think maybe this is also something like knowledge can be helpful, because we could maybe try to control like what kind of granularity of semantics that we want to convey in the like alignment, and then maybe we could have multiple granularity of alignment for each single video, so we could learn different levels together using this kind of like joint data set, and maybe it can help to get some correspondence. Yeah, I think that's very inspiring sharing. I think the last part is about the open challenge, but I'm thinking like we can also take some questions here or take some questions after the open challenge. So so if you have any questions related to the 3 topics earlier, please feel free to ask.
For large scale vision language training, the quality of data is very important. So my question is, how to define the quality of training of For example, I have very large scale into billion level crops. Then how to select a subset to have high quality to train the real learning model to achieve good performance in this market.
Yeah, so questions about how to select a subset basically of the training data to learn from. Yeah. Yeah, this often, like I'd say that like this is a really common thing that people try to look at in machine learning is like if only we could find the right data, right, then performance would work. But I think the reality is that there's never the perfect data set. You're never handed the perfect data set. And I think what a great thesis topic is going forward here is actually, how do you build these methods that can still work even when the data is not perfect? And I honestly think that, I don't know, because a lot of this is code source now, but I do think a lot of the industrial systems we see that work well are because they've curated the data set quite a lot, right? There's human curation, there's massive annotation going on. This is my guess. I'm not speaking from any authority here, but and so I think that this to really make things more efficient and make it so it's easier for another company to come in and build something is all about as kind of in academia and open research, we should be building systems that can really learn just from fully unlabeled, uncurated data. I think that's really one of the most important questions.
Mm-hmm.
Sorry, I don't know if that answers your question. It kind of punts on your question.
I can add a bit or we can move to the other question. Next question.
Go ahead, Mohit. Go ahead.
Yeah, so I know I was just saying it's a very good question, right? It's the precision versus recall balance that I was saying a while ago. I mean, in some sense, it's also a chicken and egg problem. If you knew what the best subset of the data is, I mean, you sort of have a model that can choose the best data, right? Then you've already solved the task because you're choosing training data, right, for the task that you want good supervision for. So I think, like Carl said, basically, there are existing methods that do a lot of data pruning, right, in terms of redundancy and complexity and so on. You could do some of that, but that's more for efficiency. But for cleanliness of the data, I think, I mean, the size versus cleanliness trade-off is an open challenge, open debate, and a good thesis topic, right? I think if you can figure out how to use all of the data and then maybe bring in some calibration, confidence estimation methods, right, on giving less importance to the bad data, that would go a long way. But it's definitely a kind of chicken and egg problem.
Yeah. I also want to add that, when we are trying to use select the high quality data, I think basically we need to figure out what is high quality data. So that actually related to how you can align different modalities and what is the best alignment. So if you align different semantic granularity, then the alignment score can be very different. So I kind of feel how to define what is the best alignment will also need human feedback. So there's something we could work on, when we're trying to select the data, what kind of human feedback we can incorporate in. I kind of feel for ChatGPT, they also try to learn this alignment, and they have this reinforcement learning framework trying to help the model to learn what kind of alignment is the best between instruction and the output. So for the vision language learning side, maybe the alignment, or when we are trying to find a better subset containing high quality alignment, maybe we could also borrow some feedback from humans. There's the next question.
So this is related to implicit versus explicit knowledge, and I guess symbolic knowledge as well. One of the issues with large language models is that you still see a lot of hallucination, which is knowledge that is straight up incorrect, or maybe knowledge that that is not updated and so on. So one of the topics you guys already touched upon is I guess this blend of incorporating current explicit knowledge into these reasoning tasks. So I was just wondering, like, what one is, what do you think about, like, how do you deal with hallucination correctly? And second is, what is your opinion on, like, these kinds of implicit versus explicit combinations and chain of thought reasoning models and so on?
Mohit, do you want to do hallucination or?
I didn't.
I guess.
Could you repeat the question? Summarize it for me. There's some technical issue.
Yeah, I guess the question is, I've also been wondering about this, and I don't really know the answer. Is why do models hallucinate? Why do large language models hallucinate things? What's the source of that?
Yeah, I mean, I guess the noise. I think what Jay was mentioning, right? Like one interesting direction is how to make these models reason faithfully, right? Not just correctly. I mean, it might look like a correct, reasoning chain or program, but it doesn't mean that it's actually faithful. It could have nothing to do with how it came up with the answer. So there's even more layers even after the hallucination. So it might not look hallucinated, but it could still be unfaithful. Yeah, I mean, this is again a nice thesis topic, right? Like at least a very good topic for 5 years. There's a lot of work on evaluating hallucinations. First of all, is important, right? When are you unfactual, unfaithful, hallucinate? People probably try to avoid the word hallucination just so that we don't make these models be more human or make them sound human. But yeah, so unfaithfulness, unfactuality. I think it's because of the data, right, that these models are being trained with. I feel like that's when neurosymbolic methods is a good way to go, right? You're explicitly at least making the model for, like, as I was saying earlier, right, forcing the model to spit out structure explicitly, like what was the reasoning graph or chain or path, whatever you want to call it, that it took. And this way, at least you know what kinds of errors it's making. And then maybe that can be some sort of feedback, right, in terms of, okay, this is this reasoning unfaithfulness or hallucination you made, and here is how to fix it. So that could at least give us a nice way to analyze and fix these errors, right, as opposed to end-to-end sort of non-structured models.
I also agree that part, like how to make the model not to hallucinate is definitely a very important problem. And I'm also thinking like more hypothetically, what if the model hallucinate in the same way like human? Do we feel that's a good news? Like if maybe the model is not work as well as human, but it's making the same error as human. Do we consider that kind of model to be close to human level intelligence? I guess this is, yeah, I'm also trying to think a lot and ask questions. So just wonder how you guys feel about that.
So I kind of feel for the hallucination problem for large models, as you mentioned, like sometimes the hallucination is actually what humans do. So we also kind of feel hallucination is not always bad. So when we are trying to write a fiction novel, we basically need to like ground the scenario into some background. Like we want to set the story into like last century, and then we can imagine what are the major cities in last century, and then we will also get a lot of facts related to what are the like way people transporting at that time, and what kind of house people are living in, and then what kind of clothes people will wear. So these are all the facts related to last century, and these are the factual knowledge that we want to condition the generation on. And then on top of that, we actually want the model to do hallucination, to just imagine something that is not real. So because we want to write like the fiction novels, or if we want to build a game, so we basically need some background scenario, but we need to imagine a lot of new things. And this new things is basically trying to build the like connections with some concepts that do not have connections before. So I'm not sure whether we can still call that hallucination, but that's also something related to imagination ability for large models. And I kind of feel if we want to control hallucination, it's not just ask the model to generate everything that is consistent with facts, but we need to control like to what extent we want the model to make up things, because sometimes making up things is a good thing. And I kind of feel that's a new like setting for the hallucination. So for this part, do you also have anything to add?
Yeah, kind of. Yeah, I think a good point here is combining like external knowledge source with large language models. And here we still like if we definitely not want any hallucination or try to make it less like more trustworthy in its output, a good option would be using like retrieval-based approach. A retrieval, then using large language model to summarize the retrieved results. I think that's actually used in a lot of like recent products like the new Bing or Bard, where their inputs are actually retrieved from a lot of like trusted resources and verified resources. And what the language model do there is simply by taking the knowledge from those verified sources and then do a summarization based on that. I believe like everyone agrees that large language models, they are very, very good at summarizing contents and they are quite faithful in summarizing those contents. So I believe that's something we can think about for retrieval-based approach.
By the way, Jay, just to add to that, I agree with what you said, but they are still not perfect at, there's still a lot of unfaithfulness or hallucinations, even when you retrieve a lot of information and just concatenate it together. So yeah, you can check Shiu's extractive is not faithful ACL work. But yeah, I agree with the overall point that yeah, this is what I meant by precision and recall. Like you should basically, if you only want trustworthy content, then you are limited, right? You can just retrieve from trustworthy knowledge graphs or sources, but then that's, if that's not enough, then you have to go into generating content, right? Or synthesizing is a good word, right? Or aggregating. And that's where obviously hallucinations and errors and unfaithfulness start popping up.
Yeah. So another part I want to mention is about like parametric knowledge stored in the model. So when we're trying to tackle hallucination problem, we need to borrow two sources of knowledge. One thing is the external knowledge, as Jie mentioned, like we have retrieval techniques, and for other knowledge, like the model also try to store a lot of knowledge inside their parameters. And when there's conflicts between the external knowledge and the parametric knowledge, what decision will the model make? And also when the model is leveraging this parametric knowledge, if that knowledge is wrong, whether the model can do like self-revision. So actually also related to like whether we could update the model to add some certain knowledge by editing the parameters. So there's also some study trying to show that the factual knowledge can be related to the parameter patterns within GPT-based models. So if we could find this association about how the knowledge are pieces together and how they are like reason over to get the final output and associate this kind of reasoning to the parameter patterns, then that would be also kind of a solution. I think the next question is related to chain of thought. So for the chain of thought part, I kind of feel the major problem is we are not sure what kind of supervision is the most appropriate. So basically we are able to give some guidance, trying to help the model to do slow thinking and ask the model to explain itself at each step. And then we also find like sometimes, although the reasoning chain is wrong, but the model is able to generate the correct output. And another thing is that we are not sure like whether the reasoning chain is correct when the like output is correct. So I kind of feel it's more about whether we could get the association between this chain of thought and the final output. But I think there are like basic two ways trying to improve this large language models. So we can ask the model to do something step by step to give this kind of guidance. Another thing is that whether we could directly work on the model to just find parameters or trying to just edit the model directly. Yeah. So is there anything like that?
Yeah, I guess this is also another example of what I was asking earlier. Like if the model is making similar error like human, like when we are trying to solve problems, it's also possible we are using the wrong procedure, but get the correct answer. But I guess overall, this is probably still something what we want to overcome for the large models. For this one is we probably really want correct procedure as well. And I think there are already solutions discussed earlier, and this is definitely an exciting open problem. Oh, there are.
Wow.
Do we still have time for questions about this?
Yeah. So Carl have to leave like
Yeah.
2 minutes later.
We also could just, I mean, I think the room's small. If we could make it just casual instead of a panel, we could just make it more informal.
Yeah, sure.
Yeah. Why don't we do that? Does that sound good?
Yeah, sure.
Yeah.
Yeah, sure. So, I think the tutorial will end like in 10 minutes, and I think the presenters will still stay here for more questions, and the panelists will be happy to take any questions, like more carefully. So if you want to directly ask questions to them, you can feel free to come here.
Great.
Yeah. So, yeah. So please.
Just wanted to say thanks to Emily G and Jazana for organizing everything. I think we should give them a round of applause. It's a lot of work to put together the tutorial.
Yeah, great job, everyone.
Yeah, sure. Yeah. So please feel free to ask questions if you are interested, and we'll just stay here. And others, you can feel free to follow your schedules.
Great job. It was great.
I think it was a great to I think one question was yeah, so this was all about knowledge driven, but yeah,
really lovely.
So I worked with interesting. I didn't see the beginning. Yeah, going to go for from one to another. Yeah, I think this line was interesting. News job. Yeah.
I know, yeah. Oh, I so I guess probably back to yeah, actually, you're on the graduated or you? No, I'm just still to my defense. It's good here. Okay. Probably sometimes.
I guess I can drop you an email.
还有是，就是把这些 knowledge 在一起的话，就 information， 而且上面如果我们要跟在一起学，是希望去这不光是学自己的，就是希望去有求所以像这个学 skill 啊，像学 text 或者是 skill up 是需要关心的。像这种 mix 在一起，是两个大题，我们需要考虑就是三个框架，这个是像需要考虑。text 第三个是 这些其实让这个都是一个 mix 的这些问题不能这个理解来话，因为平凡嘛，内部那个。对，现在放出来的，就是这个，哎，这里，Right, the output from the other sensitivity is这个当然去表示其他的大家比如说像 text 出出来就很难去很多，比如说像这个讲的就像在比较简单它就是一个历史的问题，去完整去表述这个它或者这个段里面它就在这个过程其实丢到了非常多的信息。如果说我们在考虑这个问题，就是用某种 modality 当成一个中间的一个媒介来进行更多 modality 去 learning 的话，基本分不上来。
Oh, no. Yeah, I just wanted to connect with you because I think we all work in a very similar domain. So, I have a WSAD paper from this year, which is like very much related to something very president. So use explicit incorporated real model as we did OKBQA, AOKBQA tasks. And now I'm working on models to kind of want to extend vision from it. So just having before, after event-based knowledge, we were looking to generate other kinds of relations, like generate knowledge from which also it could be something like what could be the intention of a person in an image, or where could a scene be located? These kinds of knowledge based on it. So we were working on like web tools, training. Hopefully these able to fine tune to do tasks. So anyway, I just thought very excited to have collaboration opportunities with you, your labs, guess you're also going to. Yeah.
Name tag.
Oh, yeah, for sure. Yes. So I'm from UBC, which is like right here. Yeah, I probably drop you. I'm just.
Yeah.
Exactly. Yeah, for sure. Okay. Thank you so much. 就是我想，我比较好奇，就是现在的话，那不是好像是身边的同事，然后我们参加同事基本上是没有这个。对，这个感觉我看可能是两个方面。那第一个是，就是这个模型可能是。RPA 整个在这个结构是一个 strong performance。哦，现在这个它这个就是大部分都是看这个，那就想怎么去设置这个去顺这个大的事情，就是它其实有很多现在的一些方法，比如说像这样的 work on the very related topic， 它是一些就是它是发掘发展Oh no, this is half person. Yeah, currently working on a model and then to kind of work. So before after but we want to kind of other donations for where we should what a person wants to do or maybe how can we yeah, very similar but I will come up with especially I guess you yeah, so one of the challenges. Yeah, one of the challenges is to how do you support and limit in the whole right. Yeah. First, you have to I mean, the module that would like sit up really steps convert so there are a lot of different work. Yeah, also work on that. I have the preference. Oh, really? Okay. Do you think that works well on very? Yeah. It's just our experience. That's really work. Okay. Even sometimes has not necessary to even thinking about it, you have to work. Yeah, like another idea I was looking at from the previous one. What if we just added like object tags? So exactly all the objects that we want to just put it into and even that is like not bad, right? But very impressive. The very yeah, indeed. Just having connected哦，对吧？这个其实因为它做起来有点太麻烦，但那个就是从原子到欧洲大概麻烦的，它就是那个毛衣，这个可能那个东西感觉或是能很顺，对吧？就是这个其实是这样的，而且还需要一些对它上面就是你怎么去
training a model 需要选择一些 comparison 的 data 来个。就你这个东西呢，比如说你才会方式，所以